All right. So today we're looking at similar solids, which very similar to any other kind of similar objects we've done. You're going to have two solids with equal ratios of corresponding linear measures, such as heights or radii, right? Basically meaning they're the same shape, but one's bigger than the other. Right? All the angles are going to be the same. All the sides are going to be in an equal ratio. Right? So we look at the pictures here. We've got a set of similar pyramids. This pyramid has the same square base as this pyramid. It's just a smaller version, and I know that they're similar because I just copied this one and shrunk it down to make the new one. And same thing with similar cones. Both have a circular base, and they're different heights, so the ratio of the diameter on the base should be the same as the ratio of the heights. And then these two are going to be non-similar pyramids because their diameters of their bases are different, but they're the same height. So one's skinnier than the other is basically the only difference. They're still the same height, so the ratio wouldn't be the same with the heights. You might have 1 to 2 for the ratio of the diameters, but 1 to 1 for the ratio of the heights. So those would not be similar. So next up, it wants us to decide whether the two solids are similar. If so, compare the surface areas and volumes of the solids. And so in this case, we want to check all of the ratios of the corresponding sides of one to the other to make sure that they all work. And so from there we're going to look and say, okay, where's the smallest side on the left one? The smallest side for the one on the left is 2, and it would compare with which side on the bigger one? The 6, right? That's the smallest one on that side. So 2 to 6 is going to reduce to 1/3. And the next size up is 4 on the left, which the next size on the right is 8, which is going to reduce to 1/2. So automatically, as soon as we recognize that we got 1/3 and 1/2, which are two completely different ratios, then we know that those two objects are not similar. And for the next set there, we compare 5 to 2.5 for the heights, which those are both the biggest ones. 5 divided by 2.5, or we simplify to 2 over 1, or 1 to 2. And then the next smaller one would be 3 on the left compared to 1.5 on the right, which 3 divided by 1.5 would be 2 again, right? So 2 to 1 ratio. And then, of course, we have 2 over 1, which is 2 to 1. So if we look at all those ratios, they're all 2 to 1. If we looked at them in the reverse, they'd all be 1 to 2 or 1 over 2. But either way, they're all the same, so we're going to have similar solids there. So first thing we want to do is, once we found out whether if they were similar, then we're supposed to compare their surface areas and volumes. And so for surface area, formula is 2 times area of the base plus the perimeter times the height. So for the big one there on the left, our surface area is going to be 2 times area of the base would be 3 times 2, length times width, plus the perimeter would be 2 times the length plus 2 times the width, or 2 times 3 plus 2 times 2, and then times the height of 5. So surface area is going to be 2 times 6 plus 10 times 5. So we have 12 plus 50. Surface area of 62. And for the other one, surface area is going to be 2 times 1.5 times 1 plus 2 times 1.5 plus 2 times 1 times the height of 2.5. So surface area is going to be 2 times 1.5 plus 3 plus 2, which would be 5 times 2.5. So surface area is going to be 3 plus 7.5, or not 7.5, 10.5. Check it myself. 2.5 times 5. 12.5. Man. See if I can get it right this time. 12.5, or 3 plus 12.5 is 15.5. So for the ratio, to compare them, we've got 62 to 15.5. 62 divided by 15.5 is going to give us 4 to 1. And then for volumes, for the volume of a solid here, we're going to have the area of the base times the height. So for the one on the left, the volume is going to be the area of the base, which we already know the area of the base is 6. So 6 times 5 is 30. And for the smaller prism, it's going to be area of the base, which we already calculated in the surface area to be 1.5. And the height is going to be 2.5. So we get a volume of 3.75. So to get the ratio, we do 30 over 3.75. Which is going to reduce to 8 over 1. So we got 2 over 1 for the scale factor, or the ratio for the sides, 4 to 1 for the surface areas, and 8 to 1 for the volumes, which leads us to theorem 12.13, which says if two similar solids have a scale factor of A to B, then the corresponding areas have a ratio of A squared to B squared, and the corresponding volumes have a ratio of A cubed to B cubed. So we started out with 2 to 1 here, and if I square those, 2 squared is 4, 1 squared is 1. So for our areas, we've got an A squared to B squared, and then if I take 2 to 1 and I cube it, that's going to give me 8 to 1, which matches up with what I should have for volume. It should be A cubed to B cubed. So 2 cubed is 8, 2 squared is 4. So that matches up with the theorem as far as what the ratios should come out to be for area and volume. Alright, so next up it gives us Two rectangular prisms have similar with scale factor A to B of 1 to 4. Find the surface area of the volume of prism B, given that the surface area of prism A is 28 square feet and the volume of prism A is 8 cubic feet. So, from this we know the scale factor is 1 to 4. And that's 4. And then if we look at the ratio for surface area, it should take the scale factor and square it, right? So it should be 1 over 4, but 1 squared over 4 squared, which would be 1 over 16. The ratio for volume should take that scale factor and cube it. Right? So we'd have 1 over 4 cubed, so 1 cubed over 4 cubed, which would be 1 over 64. So once we've got that, then we can compare using the values they give us for A. The surface area of prism A is 28. So 28 over the surface area of B should be equal to that ratio of 1 to 16. So we cross multiply and we end up with the surface area of B is equal to whatever 28 times 16 is. 448 feet squared. And then for the volumes, they give us a volume of 8 cubic feet for A. So 8 over the volume of B should be equal to 1 over 64. Cross multiply, and we'll end up with volume of B is equal to 512 feet cubed. So we're just taking the scale factor, we square it for the surface area, then set it equal to the ratio with the number they give us for the one prism that we have a number for. And the last example says 2 cubes have volumes of 64 meters cubed and 1,000 meters cubed. Find the scale factor of the cubes by finding the ratio of the volumes. So if I look at the ratio of the volumes, that's going to be 64 over 1,000, right? And ratio of volume, since we're trying to go back to the, we're going to have to find the scale factor. We know that the volumes are in the format of A cubed over B cubed. Right? And the scale factor should be A over B, right? So to go from the volumes to the scale factor, then we're just going to have to take the cubed root of both sides to get rid of all the cubes. And so the cubed root of 64 is going to be 4. Cubed root of 1,000 is going to be 10. 10 times 10 is 100. 100 times 10 is 1,000. Which basically what this gives us, going from the ratio of the volumes to the ratio that we have right now, would tell us what the lengths of all the sides were on the cube. All right. But then for an actual scale factor, we want to reduce the fraction. So 4/10 reduced would be 2/5. So that's our scale factor there.